This brings us to our third presenter, Paul Tourlonias. He is a technical consultant at IAV's battery group in Berlin, and he first graduated as a Master of Science for Automotive Engineering at French ENSTA, Brittany in 2005, and then as a Master of Science for Internal Combustion Engine at IFP School in 2006. Paul started at IAV's Exhaust Aftertreatment Components department in 2007, and over these 16 years at IAV, he accumulated many experiences with even more focus on simulation topics. Since 2020 now, Paul has been part of the Battery and Material Science Lab department, integrating battery components, testing, and simulation with deeper focus at cell chemistry. And today Paul is presenting an interesting investigation done regarding anode overhang, for which he was using GT-AutoLion-4D. Without further delay, Paul, stage is yours.
Thank you, Peter, for the kind introduction. Exactly, so after some words on my company, I will present you today a specific topic of anode overhang. The company IAV has been founded 40 years ago, so I am as old as the company today. And we are almost 8,000 engineers, employees, most of them are engineers. And we have lots of locations worldwide. Main centers are in Germany, and also one center in Detroit. So next week, if you missed today's presentation, you can get it next week also in Detroit. My colleague will take part of it. As IAV, we are a tech solution provider. Tech describes our focus on state-of-the-art technologies and development methods. Solution stands for proven ability to bring technologies to series production in full, and as provider, we proactively anticipate our customer problems and offer you our own solutions. In the field of today, our topics and session of the battery, so we are located in the future powertrain entity, and with a really high focus on energy, and especially in the high voltage battery. So now we go to the technical topic of the presentation. What is anode overhang? If you look on a very schematic view of a cylindrical cell, you will not take the time to represent the anode overhang. You will skip it because it's, I would say, at first negligible. But if you look more in details in the constructive way our cells are built, are manufactured, then you will see that there is some extra region which ensures that the anode is larger than the cathode. The reason of that is practically to avoid some edge effects in that area that would lead to increased lithium plating, which is lithium accumulation on surface instead of intercalation. So whereas the topic has been presented several times already today and will be after larger discussed also by in the next session. And the lithium plating has impact on the engine, so that's why it is important to account for that. So as some further definitions, which will be discussed further, so we have a kind of reference case, which is a case where we do not define any overhang region. Then we speak about short overhang, which is this small region in the anode when looking at only one interface or one single layer, positive, negative electrodes. And we could also speak about long overhang or long plus short overhang, which is mostly the case in all real cells. With the additional overhang region, the long overhang region, which corresponds to the boundary layers, or the last cell. If you have several cells in an assembly, then the last one will have no partner layer, so basically will stay as a kind of inactive region. and depending how many layers you consider, if you have one layer, for sure the long overrun would dominate. If you have plenty and even more layers, then this one layer effect might be negligible in comparison to the short overhang region. In the study, we had a focus on the short overhang, especially because of one, I would say, limitation of the software of GT-AutoLion-4D, that, it's only possible actually to look on the short overhang. And we made two parts in the study. So at first, we have driven some tests at the laboratory, and then we have implemented simulation. At our battery laboratories, we have built two cells of about 10 times 10 centimeters big in a glove box, starting from single-coated monopolar plates, and then ensuring that in one case we have really strict same dimension for anode and cathode, and in the other case about 10% more larger anodes and cathode. The idea there is that these dimensions are, I would say, much larger than real cases, but the intention is to maximize the effects to ensure that we see the effect after in the testing. So now one result of the testing lab is shown there. So after a fast charge or a charge phase of C3 C rate, then we go to a very long CV phase. The intention of such a long phase is to maximize the effects and to let the time to lithium ions to diffuse into that inactive region, so the overhang regions. And after that very long phase, then we do some discharge and charge cycles with repetitions to evaluate the capacity changes over these successive patterns. Between them, we put some relation time of 30 minutes, which is shown there. So looking at the overall results from the testing, so what we see and what we expect is that some lithium ions diffuse from the active region into the anode overhang region during the CV phase, and to get some homogenization of that regions. And what occurs during the discharge is that part of the lithium ions that was remaining in the overhang regions, they migrate back to the active region, so in the negative electrode, and therefore that reduces the charge capacity for the next cycle. That's why if we look at the Coulombic efficiency, we get values higher than 1, so 1.2%, which means that we have demonstrated experimentally that these regions are filled, and then after M-tight in the next cycle, and impact the SOC. Now coming to the simulation. So we wanted to look at that phenomena with GT-AutoLion, and we use for that the upcoming, I think, GT-AutoLion-4D, so maybe you didn't hear about that, which is basically a P2D model based on the classical Doi-Fuller Newman basis approach, and which is extended for some different parameters, especially the 3D discretizations that we have here to account in order to build up the geometry. We used a generic material parameter, so the intention was to first have a qualitative approach, and in a later steps, then we have the opportunities and to calibrate the model to the experimental cell. And we first did some investigation of the mesh, and we noticed that to have affordable computation times, and we had to reduce the mesh, or to really optimize the mesh. And we used, for some of the results, a kind of minimal meshing, which is shown there, where we used the overhang region to one single element. And experimentally, we had overhang region in the two directions, and we also restricted only in one direction to simplify and optimize the computation times. Here, on this kind of pictures that you will see also in the next slides, we have a factor 1000 on the cell thickness in order to see something. So all the electrochemistry is included in the AutoLion-4D cells, which is quite also important to say, because this for sure impacts the computational time. So each mesh element is discretized, and all the charge and mass balance equations are solved at each time step. Having this cell model, you need also some control logic in order to reproduce what we have done experimentally. So basically, you need the opportunity to define some CCCV phases for charging and discharging, also for doing some loops, cycling, and this is also available in that specific graphic user interface. Now I go to the simulation results. Here you see a time plot of similar scenarios than before. And it is plotted the relative capacity in ampere hour over time. And we can directly get from the simulation software the delta starting from the start of the CV phase until the end of the CV phase, so 36 hours. And we get a difference of about 2%. Which is the same order of magnitude that we observed also experimentally. And for today, I also put some presentation or some graphs representing what is going on in the cell. So here you can see the lithiation level. 0 is blue and 1, so 100% is red. Starting at the beginning of the CV phase, then we have, this is the start of the simulation, and then we have the charging phase, which is finished. So the anode is full, the active region of the anode is full, and the anode overhang region has about the same level as at the beginning of the simulation, so about 25%, 20% SOC, and the positive electrode is empty. Now switching to the time at the end of the CV phase, so 36 hours, then still we have a fully loaded active region of the anode. Still the cathode is empty, and we see some evolution in the anode overhang region with some filling, or partly filling of it, which show here a very, very slow process. And if I take a time frame a little bit later, so some hours later, at the end of a discharge phase, then as expected, we have emptied the anode region, and then it's also almost the same result in the anode overhang region, which is expected due to continuity of the results. So we have homogenization of the cell. Now, more concrete to one possible application case example. If we look at the scenario, which is a long time relaxation after CCCV charge, so which means that we have a fully loaded cell and then we switch to zero current, then we see a very slow evolution of the voltage. And we accordingly can plot the similar results for the anode overhang region, so starting from some partly loaded area. And along the time, we have homogenization of the lithiation level. And this is here the picture after 4 days, and here after 8 days. So kind of convergence of the results. This leads to a difference voltage at the end of about 30 millivolt. The interest of that is that if you do not have any overhang regions, then you would get a stable voltage, so you will not have any difference. And if you take this difference and look in your OCV curve, difference in voltage leads to a difference of SOC. So if you misestimate the voltage, yes, then you may have impact of the SOC, which means that if you let the car a long time in a garage and you measure the voltage, then possibly will do some mistake in the SOC that you would have to consider after. That's why we see here possible application cases to account for that effects in the SOC estimator. As summary and outlook, so we have verified experimentally and simulatively the effect of anode overhang by using the GT-AutoLion-4D product. Here we see that the simulation approach is well suited, especially for understanding what is going on in the cell, but also when thinking of new chemistries. If you have not the possibility to manufacture your cells, then you can at least have a first idea with simulation tools. And you can investigate then the impact under different conditions or states and vary the geometry, for example, of the anode overhang region. So we see a very challenging simulation task because you have to couple very long simulation time scenarios to observe the effects, and it has to be also coupled with very fine discretization if we want to look at these very local effects in the cell. So outlook some different points. On one side, we can have a look on the specific chemistry, so to calibrate the model to what we have measured and go on with that work. And concerning the application cases, a virtual study of the anode overhang, then for sure with the simulation we can reduce testing time and save cost by running virtual testing prior to real tests. And we can run some sensitivity studies, which can lead to some design optimization, cost or weight minimization. And what's also one possible step is to look at the aging impact. I said at the beginning, the anode overhang is linked to the lithium plating topic and aging. So once the environment is set up, we can really then also look at that. And we can also imagine to populate, to derivate some simplified models, maybe 1D or basis, to integrate in the BMS to account for that. Thank you for your attention.
Thank you so much. Very interesting topic and great presentation.